Today we're going to cover simplifying radicals and rational exponents. Rational exponents, another word for that is fraction exponents, which are it's a very important topic for pre-calculus. I want to get right to some examples. First thing is scientific notation. I don't think I should have to spend a lot of time on this. I'm just going to kind of refresh your memory. You know, if I have something like 0.0000782, and I was asked to write that in scientific notation, well, what we do is put the decimal after the first non-zero digit, make it 7.82. Scientific notation is always times a power of 10. And then if it is a decimal like this one, it's going to be a negative exponent, and then we just count back. 1, 2, 3, 4, 5 to the negative fifth. All right? So I think you all know how to do that. I'm not going to spend a bunch of time on it. What I'd rather get to is get started with simplifying radicals. And you're going to need those root sheets I gave you. They're going to need to be out on your desk because otherwise it's going to be difficult to simplify. So you all remember square roots, something like the square root of 36. We say, what is the number you multiply by itself to get 36? And we know that's 6, and you can see that on your root sheet. Now, where we have to do a little bit more thinking is if I have something like this, the square root of 72. This is where the root sheet comes in handy. We look within this number, 72, we look for a perfect square. So you look down the x squared column, and do you see a number there that is inside 72? What is it? No. Wouldn't it be 36? Isn't 36 times 2 72? See, we can write this as the square root of 36 times the square root of 2. We have to be able to multiply a square root, okay, a perfect square, which 36 is what we call a perfect square. All right? And I can break that down or factor it into the square root of 36 times the square root of 2. And then we're basically done because what's the square root of 36? 6. So this is 6 radical 2. Okay? Now, you try one. I'll do an easy one. How about the square root of 50? And I'll pause the video. Okay, good job with what I saw. This becomes the square root of 25 times the square root of 2. So it's 5 square root of 2. All right? And obviously, the reason for the root sheet is sometimes they're not as common. You know, if you were to see one like this, let's say that I had the square root of 147. Now, that one's not as easy to see as the last two. But you don't want to think, well, I can't do anything with that. You want to start going down your list of perfect squares. Obviously, can't I eliminate the even ones? You know, it's not going to be 4. It's not going to be 16. It could be 9. But you want to divide this by those perfect squares until you find one that works evenly. And you want to use the biggest one you can. All right? So, if you work down through these, I think you'll find that this is the same thing as the square root of 49 times the square root of 3. Okay? And you just work down through your list of perfect squares and find one that works. You know, you could take 147 divided by 4. Well, that's not going to work. 147 divided by 9. Maybe it does, but you want to use the biggest one possible. This is 7 radical 3. Okay? Sometimes you might see something like this. The cube root of 125 over 64. Now, here's the good news. We can break this up into two radicals. I can make this the cube root of 125 over the cube root of 64, like that. And from here, you can use your root sheet. Now you're going to look down the perfect cubed column. Do you see 125 there? So what's the cube root of 125? 5. The cube root of 64 is 4. There's your answer. All right, so you just break it into two. Lots of different situations. I'm going to try to cover as many as I can. How about the fifth root of negative 32? Can I take the fifth root of a negative? I sure can. I can take the fifth root of a negative, but I can't take the square root of a negative. All right? Or any even power of a negative. We'll learn about those later. So this is okay. So now you just treat it like it's a regular number. Do you see 32 down the fifth column? What is the fifth root of 32? Isn't it 2? But since this is a negative, this is going to be negative 2. All right? Because if you raise a negative number to an odd power, you get a negative number. All right? Think about it. Negative 2 times negative 2 times negative 2 times negative 2 times negative 2. Those two make a positive. Those two make a positive. And then you got your negative here. Okay? Positive times a negative is a negative. All right? Lots of different ways these can look. Let's go to this one. How about the square root of 8 times the square root of 2? Can I multiply underneath radicals? Can I multiply the 8 and the 2? I sure can. So this becomes the square root of 16, which is 4. Okay, just multiply under the radicals. Be a good idea to keep your notes handy tonight. See all these examples. How about the cube root of 5 cubed? If you see this, you'll say, yay, I like this one. It's just 5, right? And this one's 5. That's easy. How about the fourth root of 48? What we're going to do is we're going to treat this just like before. Do you see a perfect fourth that's in 48? Somebody said it, 16. This is the same thing as the fourth root of 16, right, times 3, right? Or we could think of it as the fourth root of 16 times the fourth root of 3, whichever way you want to think of it. So the fourth root of 16 is 2, right? So this would become 2 times the fourth root of 3. Just like that. If you need me to slow down, just ask. But like I said, there's a lot of different situations we need to get over. How about the square root of 75x to the third? Now, once again, we are looking for perfect squares. All right? Now, it's probably a good idea for me to come over to the side now and talk about x squared. Is that a perfect square? Is x squared a perfect square? It is, isn't it? What's the square root of x squared? X. So that means it's a perfect square, right? So what we're wanting to do is break this thing down so that we have a perfect square times something. Do you see a perfect square in 75? Isn't it 25? So I want to make this the square root of 25 times the square root of 3. That takes care of the 75. Now, let's look at the x cubed. Didn't you just tell me that x squared is a perfect square? Can't I write this as the square root of x squared times the square root of x? Isn't x squared times x, x cubed? Right? All I did was break it up a little bit so I could get a perfect square. So look what I've got. I have a perfect square here and a perfect square here. Those come out. So what's the square root of 25? 5. What's the square root of x squared? X. Everything else stays under the radical. The square root of 3x. Okay? Let's do another one of those. How about the square root of 128 x to the 5th. And I'll pause the video. All right, let's see how you did. 128 becomes the square root of 64 times the square root of 2. With x to the 5th, we want to break it up into an even power times whatever's left. So the square root of 64 is 8. The square root of x to the 4th is what? X squared, very good. Everything else stays inside. The square root of 2x, because those things are not perfect squares. They can't come out of the radical. Okay? Let's do another one. How about the cube root of 24a to the 4th? Well, now we're looking for perfect cubes, right? So if you look down your perfect cubed column, I think the first one you see that will go into 24 evenly, or the largest one that will go into 24 evenly, is 8, right? So I can make this the cube root of 8 times the cube root of 3. Right? Now if I'm doing a cube root dealing with this a to the 4th, then I want my power to be a multiple of 3 instead of a multiple of 2. Right? So couldn't I make this the cube root of a to the 3rd times the cube root of a? What I'm wanting is to get, the power, the root, and the power under here to work together. Okay? So the cube root of 8 is 2. The cube root of a cubed is a. Those two come out. Everything else stays under. The cube root of 3a. Okay? After you do, you just have to trust the system. It does work. All right? Follow the notes. Now, we need to get to rational exponents before we run out of time. Rational exponents are ones where we have something like this. And I'm going to go straight to an example. Let's say you're asked to evaluate. Something like, and we're going to do this without a calculator. Something like 27 to the 2/3 power. Now, this really isn't that bad. We just have to understand the flip that happens. Here is my root. This is the same thing as the cube root of 27. So you start here and work this way. The cube root of 27, that whole thing is going to be squared. And that's how you deal with a fraction exponent. What is the cube root of 27? 3. So this is the same thing as 3 squared, which is 9. Okay? Fraction exponents are really not that bad once you understand the flip. Let's do another one. How about 49 to the 3/2 power? Well, you always start with the root, which is right here. This is going to be the square root of 49. That whole thing is going to be cubed. So the square root of 49 is 7. 7 cubed is, from your root sheet, what is it? 343. Now, what if you get a negative? Like 16 to the negative 3/4. You do everything the same, you just do it in the denominator. Okay? Because this negative means you move it to the bottom. So it's just 1 over 16 to the 3/4, and then you just follow that little flip. Okay? One last thing before you go about rationalizing the denominator. Do you remember this? 5 over the square root of 7. How to rationalize that denominator? Multiply the top and bottom by the square root of 7 over the square root of 7. And the reason we do that is that would give me 5 radical 7 over, this just becomes 7. Okay? So that's rationalizing the denominator. You'll have to do that a little bit. And we will stop there for tonight.